Before we go through the two examples, as I mentioned, the low mass and high mass, relative high mass stars at the main sequence, I wanted to remind you what we found actually in the previous lecture. In previous lecture, based off the equations which they defined the luminosity energy rate or energy generation rate and the other quantities, and by assuming that the opacity remain constant, we found that the luminosity is a function of the mass and chemical energy or chemical potential, as you see here, and the radius is also a complicated functions, power law function of the mass and chemical potential, and the temperature at the core of the star is also given as expression with the power of the m and power of mu. As I mentioned, we can use this equation for two reasons. Actually, one reason is that you can think that how the luminosity, radius, and core temperature, which they have the same compositions, or in other words, if you can show me two stars which they have the same chemical potential or same chemical composition at the core, then those equation gives you the dependence of the luminosity, radius, and core temperature as a function of the mass. And second things which you can do with this equation is that you think about a single star, one star, and by single star we mean a star which you fix the mass, and then you can see the change in the luminosity, radius, and core temperature as a function of the chemical potentials. And you can study that when the chemical compositions of the core of the star change, so how the luminosity, radius, and the core temperature will change. So we are mainly talking about two classes of the stars. So one is the star with low mass. They are the star at the mass at the order of the solar mass. So any star which located close to the sun at the main sequence is considered as a low mass star. And for low mass star, those index, this index is given by digit 4. For higher mass star, the mass of the star which they are greater than or equal to the mass of the solar systems, the energy cycles is Cno, as we discussed in the first chapter, and also you studied in your previous course of the Physics 3901. So we are going to show you that how for those type of the stars we can get some informations from the scaling relations. To do that, we actually focus on the example. So this example is about to finding some information from the scaling equation for low mass star. Low mass star are the star which their mass is at the order of the solar mass. So if the mass of the star is in the order of solar mass, the index of the nu is given by 4. Then if you go back to the equations which we have, so we name it the equation 4.6, like the equation which gives you the luminosity just by substituting the nu equal to 4. You can show that the luminosity is proportional to the cubic m and quadratic mu. And because it is about the single star, so there is no change in mass, so you can say that because it is low mass actually, so low mass stars, so the energy change or proton change dominated. So I mean the chemical potential for them is a constant, so you can show that the luminosity based on these calculations is proportional to the cubic M. Furthermore, for temperature at the core, you know that the core temperature is given by m power of 4 over nu plus 3 and mu power 7 over mu plus 3. If you fix nu as a 4, then you can show that easily that it will reduce to the 7 over 7, so it will be mu actually power 1, and here you can have m power 4 over 7. And because I mentioned that for low mass star, the mu is actually constant, so you can see that the core temperature will be proportional to the mass power 4 over 7. And then for radius, you can see that the radius of the star are proportional to m power nu minus 4, nu plus 3, and nu minus 4, nu plus 3. And if you set here nu equal to the 4, you see that the power of the mu will vanish, so it will be mu power 0, which means 1. And here you will get m power 4 minus 1, 4 plus 3, so m power 3 over 7, or m power 0.4. This is very important results, and it suggests that the luminosity actually increase very steeply with the mass, as you see, because it's m cubic. Core temperature increase somehow also with the mass, as you see, but not very sharp or fast, and the radius will be proportional to the m power 0.4, which is not also very high power. Those calculations are very important actually, because if you want to study the evolution of the any star in the main sequence with lower mass, so those equations, after you solve all the equations, those relations help you to understand that are you going in the right direction or not. So you can summarize actually what we did it here. We can summarize what we did it here. So if you think about the mass in the low range mass, so for low mass stars, the dominant energy source is proton change, and the exponent here, nu, is given by 4. Remember that in all our example, we consider opacity as a constant, so there is no any change in the kappa, or kappa is not function of the mass or chemical potential, whatever. For high mass star, when mass is greater than the mass of solar system, so the dominant energy source is Cno and nu is 17. So if you back to the equations and just substitute the nu, so you can see that the luminosity and temperature at the core and radius will be proportional to those. This example done when you have a type of the star with the same compositions. So if you believe that the star in main sequence, some of them have only pp proton change, so then you can think that about that the chemical composition inside the star remain the same. I mean, mu is constant, so then those expressions gives you the change in the luminosity, core temperature, and radius as a function of m. And for high mass stars, the exponent is high, nu is 17. So then those expression gives you also the expression for luminosity, core temperature, and radius. Any question about this table? But I raise a question for you. So you see the low mass star, radius is depend to r power 0.4, and for high mass is depends 0.8. So is it possible you tell me that in which of these cases, I mean low mass or high mass, in which case the radius will change more by the change of the mass? In which one? If you put some mass, if you add some mass to the star by any process, for example, then which one of these stars, low mass or high mass, have greater chance to increase the radius? This is actually, for example, the second equation, for example, is for high mass. High mass, this is the equation for high mass. You see that this is for low mass, actually. This is for high mass, and this is for low mass. You see, if you increase, x is m, actually, m. If you increase the mass, you see that somehow there is a point that the lower mass stars and higher mass stars, they have the same behavior. And after that point, if you add a little mass, you see that the high mass star, the radius for that will increase very much than the low mass stars. So, for example, if you just imagine that if you add some mass to higher mass stars, so the chance to have greater radius or greater size for the star will be more than the low mass stars. And it is possible to see the difference of them. I mean, the difference of those two functions. I know that they are actually a proportionality, so they are not a real expression. So just imagine that I wanted to see the difference of the mass just between the lower and the great. So this is actually the difference. So see, the difference between the mass is also very strange. So for very low mass stars, as you see, there is no difference between low mass and high mass. And somehow when the mass is increasing, so the difference between the star will be very significantly. You see, this is for high mass and this is for lower mass. And this is a difference. So difference between two stars will be very, very high, actually. Okay, now we are going to the case that the mass of the star is now fixed. We are talking about the same type of the stars, but we are going to talk about the two of them which they had a chance to have a different chemical compositions. And now I raise the question that how the luminosity, core temperature will change versus the chemical potential or chemical energy or chemical compositions for a single mass star. If you go to the questions which we developed for low mass stars, actually, again, the index of nu is 4. So if you go to the questions, the scaling questions, you will see that the luminosity will be proportional to the m cubic mu4. And if you fix it the mass, so it will be proportional to mu4. I want to do one things, and the things which I want to do is let's go to see the three-dimensional plots, which they are very interesting and will help us very much. For example, look, I call Z, but you can call whatever you want. For example, the luminosity, and luminosity is for lower mass stars is proportional to m cubic, as you see, times mu power 4. All right. I want to plot these functions. If you, what's happened here? No valid equations, no valid range. All right. There is a problem with the range, so let me to back it to the, I consider mass as x and chemical potential as mu. I hope it will work. So you see this beautiful three-dimensional portrait gives you the evolution of the luminosity for low mass star for a general star with a different mass and different mu. So now if you fix it the mass, so then it will be proportional to the mu square. All right. And I wanted to add another equations. The question which I will have is about the temperature. So how the temperature will change? You see the temperature will change like m power 4 power over nu plus 3 and mu. So if you set nu 3, so you can see that 4, sorry, mu will remain linear and mass will change like mass will change like m power 1. Mu is 4. Okay, 4 power 7, sorry, 4 power 7. So x power 4 power 7, or 4 over 7, times mu is the power 1, so let's see how it works. This is the second. This is the change of the core temperature for low mass star. It's very complicated pattern of the core temperature versus the mass. If you wanted to show the frame, so maybe that will be very helpful. So the x-axis, we consider here the x-axis is the mass, the y-axis is chemical potential, and the z-axis, we show the z-axis as a core temperature. And then about the radius, it's very interesting that if you consider the radius as a three-dimensional functions, so the radius for low mass stars, will be m power nu minus 1, nu plus 3. So if you set nu 4, so 3 minus 1, 4 minus 1, 3 over 7. So, and there is no any 3 over 7. And we are surprised that there is no dependence of the chemical potential for low mass stars here. This is the radius. So I can write nu power 0. Yeah, run nothing. This is what happened. So as you see that it shows that the radius doesn't change with chemical potentials if you fix the mass. I mean, if I fix this, so the surface of the z equal to 1 will be that, you see, will be that, and it will be very interesting. So if you fix the mass for a single type of the star, changing the chemical compositions doesn't change the radius. Okay, again, I will back to the expression which they defined the luminosity core temperature, radius, and chemical compositions. For mass star of the low mass, when nu is 4, and when the source of energy is proton-proton change, the results from the scaling equations of the stellar revolutions gives you luminosity, the function of the mu q quadratic, core temperature, linear function, and R gives you constant. And for high mass star, the luminosity is proportional to the chemical potential quadratic, as you see here. Core temperature is some fractional power of mu, and radius is some fractional power of the mu. So if they give you any questions that they are talking about the star that they fixed the mass of that star and it has the constant radius, you can say that this star is low mass. And if it changed by the chemical potentials, then somehow you can say that it's a high mass star. Any question about here? We are going to the next part of the lecture. We are talking about few slides, and then the lecture will end in the Wednesday. So hopefully this chapter will end in the Wednesday because we go very slowly. I don't want to run on this subject because it's a bit hard to study. Okay, so what was the question? The question which we started to study was that we wanted to know the time actually that a main sequence star will transit from main sequence to the red giant. And this is a question which is related to the age actually of the stars. So, and it depends not only, it depends also the process of the energy which is going inside the core of the star. In low mass star, as you know, the pp change, proton-proton changes dominated dominated strategy for energy generations, and for high mass star, the Cno process is the dominant one. What is the Cno process? So a high hydrogen is converted to the helium, and the mean molecular mass and core temperature will increase. So during the process of hydrogen to helium, the mean molecular mass is increased and temperature will increase. Why temperature will increase? Because you see temperature always changed by the mass as a power, if you're back to previous slide. If you increase the temperature, so you get more chance to Cno cycles to be the winner of the battle for energy generation in comparison to the proton-proton change. So you can say that the Cno cycles, why it happened? Because among the two processes of Cno and pp change, the Cno is the one which is very much dependent to the temperature. For Cno cycles, the energy is proportional to the power 17 of temperature. And this is give a huge amount of the energy if the temperature is increased. It will affect also the energy generations. It will push the energy generation to happen in the narrow shell, and this narrow shell is sandwiched between the burnt helium interior and the cooler regions. You remember the burning helium was a parameter which by that you can estimate the age of the stars. This condition is called shell hydrogen burning, and it happened at the age, as you see. And if these conditions satisfy, so burning by the Cno cycles actually will be more important than the pp chain at the higher temperature. So what you understand is that the Cno cycles is preferred to the pp chain because when the temperatures increase, the energy related to CNO will change very much as a higher power than the T respect to the temperature. But to give the more estimations and to explain that what is this shell hydrogen burning, we need to solve those equations, the equations of the stellar revolutions numerically, and that's very hard things. And if you do the numerically, then you can estimate it, actually the luminosity, and then from the luminosity and from the other equation, you can estimate it at the energy generations, and finally you can get the idea that how the energy generation scale it with the temperature. There are some things which we have to say that in the star which the helium-rich core is just helium-rich and still not mixed with the hydrogen. So this kind of the sandwich process or existing of this shell hydrogen burning is actually it's not very easy to talk, and it's not static. I mean, will be changed by the time. Especially the numerical solution and simulation show that for low mass main sequence stars, which they have the convection zones out there, the outer layers actually play the more important role than the other regions. So if the stars become a little cooler, so then it becomes more convective. I mean, the process of the lifting the energy by convection process will be more effective, and then it approached some limits which we call it Hayashi limit in Hertzberg-Rosen diagrams. So let's to show all in the one example. So this is the example, for example, show that the evolutionary tracks of the star with the spatial range of the mass, because this to solve those equations, you have to specify the range for your parameters, and one of the variables in the equation is the mass, and you have the gradient of the mass in the equation. So you have to know that which regime or which interval this mass is changing. If the mass is changing between 1 to up to 9 solar mass during hydrogen burning, then this is what is going to happen. If the mass is changing between the 1 to 9, so the effective temperature, which is not the core temperature, effective temperature was the temperature of some outer layers of the stars, it will change between the 40,000 to 2,000 to 2,000, actually 2,500 degree Kelvin. And luminosity will be changed, like, as you see, very drastically. So, and there is a Hayashi regime. I mean, Hayashi regime is the regime that the effective temperature is very high, and it seems that most of the stars with this range, with this mass, they have a profile of luminosity versus the effective temperature will be end asymptotically to this limit. So this is like asymptotically slope of the line, so it is dashed line, which you see here. All right, from all of them, what we understood is that the cycle CNO energy generation rate is power 10, T power 17 actually. We talk about CNO, but not very much here. But we can say that the energy production is actually is very complicated process. So and the CNO cycles, it's not continued after for any range if the star reach a special radius. So if you're going a little far or at the large radial distance, so then the CNO cycles will vanish. and this will affect the elements which they exist in the stars. So this effect that the CNO cycles will nevertheless be active over a large radius than spatial distance. So it will call it the effect of abundance of the CNO isotopes. And actually, what we call about CNO is a cycle that converts the carbons to the carbon 12 to the isotope of carbon with 13 and to the nitrogen with 14 atomic numbers. And it will happen in the star when the temperature is very much increased. This diagrams gives you the element abundance and fraction of versus the fraction of enclosed mass. I mean, enclosed mass means that the mass of the elements which compose the star. So yeah, you remember we defined the fractions before in the previous lectures. So if you consider the fraction of elements, I mean the ratio between the elements, like that. So, and this is the element abundance. So you see that for the blue graph show you the change in the nitrogen, actually, the star which made only by nitrogen, and as a source of the, I mean, in the part of the CNO cycles, the portion which is related to nitrogen is the blue one, and it showed that the element abundance actually is decreasing when the fraction of the elements are increasing. And carbon have a strange type of the behavior that when the fraction of enclosed mass is increasing, I mean when the ratio between the elements is increasing, so the element abundance will reach a constant value, so asymptotically. And the oxygen actually has a similar behavior like carbon, but it started before. Actually, the nitrogen and oxygen will started at the fraction before the fraction of the enclosed element reached 0.2 or 0.3. So, and carbon is the one which is start very late, actually, you can say like that. So abundance, element abundance actually has significantly changed by the fractions of the mass, and for oxygen and nitrogen, it will start in very low fraction rates. What is the convection? So convection is some type of the mechanical dynamical motions in the fluid, which if the fluid is set in the gravitational field. It is actually based on the difference of the pressure or difference of the density from one point to the other point. So if the material density be less, so the convection will be increasing, and it will be vice versa for the material with high density. It's like a lifting, you know, if the fluid is lighter, so the lifting of the fluid will be easier, yeah? So convection will be easier for the fluid with lower mass. Usually the density difference is related to difference of temperature from thermodynamics, you know that. And because of that, it looks like the fluid is moving from the lower temperature to the higher temperature, right? Because density is proportional to the temperature. And for lower density, you have a lower convections, and for higher density, you have a more stronger convection. So convections can be is a mechanism, actually, one of the mechanisms for transfer the energy. Even if you, for example, living in this two-floor house, for example, you know, if you turn on the AC and in the base or in the first floor. So then it will be cold. You know, after some time it will cold to the temperature will be changed at the second floor also, or vice versa. So those change in the temperature depends to change of the density. So if you have a lower density, so then the convection will be faster for you. The reason is that actually a hotter layer is prevented by high opacity. I mean, it is supported from the high opacity, like shining or cooler layers, but the radiations is prevented by heating up by the cooler layer. I mean, so each this is not very maybe clear statement, but we can just say that what is related to astrophysics, we can say that star convection in the star in astrophysics is one of the parameters which make the star will be unstable. Yeah, right? Because it's like a transfer of the energy. It's like a radiation. So you know that the radiation always make the systems unstable. This is a pictures which we can talk about the convections. You see that the opacity is very important. Opacity was like a capacity. You know? It was a possibility for one object to be dark. If something is not, it is not very dark. I mean, if it has a low opacity, so when you make it hot, this convection process actually lifted the hot temperature to the upper levels, and upper levels will be warm. And finally, if you go very far, of course, it will be cold again, cool down for low opacity, for something which is not dark. For dark regimes or darks with the star, when they have a high opacity, actually, when it becomes hot, so the hot will be warm again, and I want to tell you that the time which the star will be cool will be shorter than the time which a low opacity star will be cold. So the stars which they are not very dark, they will be cold longer than period than star which they have a high opacity. So dark star will be cool faster than the light star because of convection. Because it is related to density and other things. I explained that picture, so no need to go again to that paragraph. So what was the problem? The problem was that we want to estimate the time that the star will move from main sequence to be giant. Okay, the interval which the star moves actually to the right in the Hertzsprung-Russell diagram is called subgiant phase, the time. Okay, so when you remember the Hertzsprung-Russell diagrams. If you don't remember, I will show you HR diagrams. That was the Hertzsprung-Russell diagram, is one of these. All right. That was the Hertzsprung-Russell diagram. You see, we are talking about when the main sequence star, lower mass or high mass. Those are high mass, lower mass are that, like that. The sun is here. They will jump to the red giant. To be giant red giant, so it's a region called subgiant. So first they have to pass this step and be in the subgiant region, actually, or the group of the star, which we'll call it group of 4. If you remember the physics 3901, Mysteries of the Universe. So this is called a subgiant phase. This is intermediate. And as the envelope expansion is because this process is quite rapid, so stars are in this phase for very short periods. Short period in comparison to what? In comparison to their age, and their age is calculated based on the main sequence hydrogen burning time, actually. So you can say that finally very few stars actually you can see in subgiant stage of evolutions. Most of them will be jumped to be giant, actually, to be giant. And some of them also get the chance to be supergiant. So they are going to be graveyard. They are going to be in the die, actually, as you know. They are going to be die in the graveyard of the stars. So this gap between the main sequence and this giant star is a supergiant phase, actually, which is very short. It's actually it's called a supergiant phase, as I mentioned, and it makes a gap in the Hertzsprung-Russell diagrams between the end of the main sequence. I mean, the main sequence will turn off, and then the star will be turns to the red giant branch. So this is called a Hertzsprung gap. So this is the Hertzsprung gap, you can say. This is the Hertzsprung gap. So there is no information. I mean, you can get it from the Hertzsprung-Russell diagrams because it's based on the information for main sequence and other estimation for white dwarf, brown dwarf, and supergiant. So there is a range that you don't have any data actually, or because this is a transitive phase, yeah. So this is called the very transitive phase, and that makes a gap actually. So you have an island actually. You have one island here, one island, you see, and between them is like an ocean. You have the water here. This is called a Hertzsprung gap. So again, you will see here. So this is a main sequence stars. You see some contours plots. Actually, this is a contour. So I mean, everything's existing. This line has the radius of 0.1 solar, and everything's related on this line has exactly solar mass. Everything which exists on this line has 10. Those called contour. So, and there something else here. You see there are many other things. So the Hertzsprung gap actually is like a filling these islands between with the oceans. So that looks like that. And this is, as I told you, this is a transitive regime, and it makes a lot of so I want to tell you that there is a regime of the star that they are unstable here because they don't know what to do. So they are unstable. So and in the subgiant phase, actually, there are instability, and the star which they are living there are actually they are trapping in the instability strip. Strip means this strip. You can, based on the mass, you can name it them different things. So, for example, you can do Scottish stars. They are the one which there are subgiants with the mass of the order of 2 times of the mass of solar, or you can have a dwarf. Dwarf are also somehow belongs that to the subgiant phase, and there are binary systems and whatever. You know, one of the main discoveries about the gravitational waves was given by the detecting the gravitational noise signal came from the far times when a binary merge. So it's not important. It's not very correct that they are not important. Actually, the trick to trap them is very difficult. To trap everything which is in the subgiant phase is very difficult actually. So So that was the difficulty to detect the gravitational waves, because it comes from, theoretically, it's one of the best candidates. It will be the binary merge, actually. I want to keep it this few slides for the Wednesday. So, and now I want to let a little bit talk about the homework which I gave you, the simple things to do. So did you complete that? So and we have to discuss the rest of the talk now about these homeworks.